Welcome back in, everybody. Today we're hopefully going to draw breasts one last time as we take a look at the Stark effect. Now what the picture is, once again, round thing with the dot in the middle, and we want to say we're exposing it to an electric field, and this induces some dipole moment on the atom. But instead of looking at this from the classical equations of electrostatics, let's see if we can take a look at quantum mechanics, see if we can apply that. So in order to do that, we got to use this technique of perturbation theory, where we have the normal Hamiltonian for the hydrogen atom, which we're going to call H0, and we're going to add on some small delta H, a change to the potential. And this delta H here is going to be the interaction energy between the electric field and the dipole of the atom. So the equation for that, isn't that hard to show, energy of a dipole interacting with an electric field is minus P dot E. So if we translate this into quantum operators and plug that in, then we can get our delta H, or the small perturbation that we're going to make to the standard Hamiltonian of the hydrogen atom. Now don't worry if some of this formalism doesn't make sense. We'll circle back and do the hydrogen atom problem in a later video. So if we go through and solve the normal Schrödinger equation using the standard Hamiltonian H0, and we act that on a state psi n, we get some energy come out, En, and I will label it 0, just like I meant to do over here, to show that it's just the 0th order energy multiplied by, of course, the same psi. Now this is a ket representing a state, whereas if you draw it from the other side, that's a bra. But we're not dealing with bras right now, even though that would make sense. Sticking with the kets, H0, E0. Now for the hydrogen atom, those energy levels are pretty easy. Minus 13.6, roughly, electron volts divided by n squared. N's just this quantum number. It tells you what state you're on. If you're at the ground state, n equals 1. Minus 13.6 is the answer. N equals 2. You're in the first excited state. It's 13.6 over 4. It's about 3 electron volts. That just gives you the energy levels of the hydrogen atom. But now we're going to perturb that a little bit, and we're going to see how it changes. So the basic premise in perturbation theory is that if we take H and we write it as H0 plus some small correction, the energy, which initially was just E0, which is what we had before, is now going to get a series of correction terms. First order term, second order term, plus an infinite number of them. Just by making a small correction to the Hamiltonian, we get an infinite number of corrections. This is the one we've already solved. These two we're going to go after right now and see how it corrects. Because these are the leading order terms, by far the most important. In fact, really only the first order term is the most important. Everything higher than that, we could chase it down if we wanted, but it gets increasingly harder for less and less important information. I just realized I didn't address the words I had at the top of the board. So Mr. Stark, like Tony or Ned or Bran or such, was a scientist, except he was a Nazi. In the early 1900s, he came up with this effect that you can lift the degeneracy of the hydrogen atom or of any particular electron states by applying an electric field. So that's why it's called the Stark effect. But we don't need to give him too much credit. Okay. I return. So the standard equation for finding the first order correction to the energy in perturbation theory is you take a state, and for the hydrogen atom, the state is defined by three numbers, Nl and M. And this here is a bra. So you take the bra and you unclasp it, and then you sandwich it with the perturbation to make a little sandwich. And then you put on the other side of the sandwich a ket with the same N, L prime, M prime. And the reason they're primed, I squeeze that in there, is because what this represents is actually a matrix made up of all the different combinations of L and M. So you'll have a bigger matrix depending on how many possible states there are. And of course the number of L's and M's is set by a given N. So an example, in the ground state, N equals 1. That is one state. So it wouldn't actually be a matrix. This would just be one number. Because at this state, L's got to be 0. M's got to be 0. So how we write that down, the bra portion, 1, 0, 0. The perturbed potential, delta H, and then 1, 0, 0. That's just a number. That right there is the first order correction, E1, 1, of the ground state. And if we go back to what delta H was, delta H minus P dot E. Now if we say the electric field is just oriented in the Z direction, so E equals some magnitude Z hat, this will simplify to be simply minus the electric charge, the magnitude, and then the Z operator. So we can plug that into the equation for delta H with these terms just hopping out front. And we get this. Now, what's interesting about this is this will end up being an even function, and this will end up being an odd function. So the whole thing will be odd. And what this matrix element means is to integrate from minus infinity to infinity whatever's inside over volume. Now the problem with that is if you integrate an odd function over symmetric bounds like this over all infinity, it'll just go 0. So that means to first order, there is no correction to the energy for the ground state. So that's exactly what the answer is. E11 equals 0. Now if we want to consider for a minute n equals 2, we can track that down as well. That would be E2 to first order. We get a similar expression. We factor out minus E magnitude of the field. This time 2 Lm, the Z operator, and then 2 L prime M prime. Now we can go through the math of here. Now since n equals 2, L and M can take on a variety of values. And as a result of that, the energy actually splits to be plus minus 3E electric charge, magnitude of the electric field, and it gets multiplied by the Bohr radius, A0, which is a nice thing to have come out. But the question is, there's two energy levels now, whereas previously it was just one. What are the eigenstates for these energy values? Well, in fact, you might think that it splits nicely to the 2s and 2p orbitals. But that's not the case. What we actually have is a mixing of both of these states. So the higher energy is a combination effectively of the L equals 1 state plus the L equals 0 state, and the lower energy is the L equals 1 state minus the L equals 0 state. Those end up being the two eigenvectors, which the higher energy corresponding to the positive and the negative energy corresponding to that. So these are the corrections to the first excited state to first order. So if we want to now track down the second order correction to the energy for a particular state n, we get an actually bigger equation. So we actually have to sum over all n even higher than the one we're interested in. So it's a bit more difficult to track down, but it can be done. So we have a bigger equation here. We have, again, the bra-ket sandwich. And if you didn't figure out where that word's coming from, bra-ket, and the thing in the middle that gets sandwiched is just a C. That's bra-ket notation. Mr. Dirac thought that was quite a fun way to phrase that. But anyways, you take the psi for a particular n, you sandwich in pi ei, which is just the energy that we were talking about under correction, n prime. Then you do the same, but flip it around for some pj ej psi n. And I can't quite finish the ket. There it is. And you actually have to divide by the energy difference for a particular state. So the zeroth order energy of n minus n prime. Now that looks like a mess. We have now an infinite series of multiple matrix elements to compute. We have to find these energies. Oh, it's just a mess. But it turns out we can sweep a lot of that under the rug if we just say, define this dude, alpha aj. So this is going to be a second-rate tensor indexed by an I and a j. We'll write it down real quick. This is going to be kind of a definition for us. The same sum. And we're basically going to write exactly the same down. But, so I'll just drop some of the things. I, and then the psi, and then the pj, and then the psi, over the energy, n minus energy, n prime. Sure, I'll put in some zeros. So this is the thing you actually need to spend some time in calculating. But this has actually already been done for a lot of atoms. This is our old friend, the atomic polarizability from the previous video. And we know from experience that this alpha ij can actually just be reduced to a constant alpha 0 times the Kronecker delta. Don't worry about that. That's just to convert a constant number to make it fill up a big matrix, but whatever. It's actually just sort of a constant number, depending on the material, right? It's a particular value for hydrogen or for all the other atoms. So this really simplifies quite nicely. What would be left over? So we left the p's in here. We have two copies of the E in there. Don't be confused. This is the electric field E, to be distinguished from this E, the energy. So it'll just be the magnitude squared will pop out. We'll have this factor alpha, exactly one time. We'll just call it the alpha 0. And because of this factor 2 in the definition, there's actually a minus 1/2 has to fun around. That's actually the answer. This is the second order correction to any of the states. That's a funny looking E. It's got 3 nubbins. Can I finesse it? Can I finesse it away? Chalk's weird sometimes. But that's it. This is just going to lower all the energy levels by this amount, proportional to the square of the electric field's magnitude. That's the second order Stark effect. Thanks for watching.